Okay, it's 11, so let's get started. I just started the iClicker session for our class, so you should be able to join it now. Couple of announcements. If you haven't watched the recorded lecture in place of our in-person session on Friday, you should have watched that already. So make sure you watch that as soon as possible. I have directions in a Blackboard announcement of how to access it. I am assuming that you all have watched that, so make sure you all watch it if you haven't already. The next Achieve homework will be posted either later today or tomorrow, so that will be the first part of Chapter 2. And then our first unit exam is next Wednesday. So just keep that in mind. We have a little over a week now, and I'll have more information about the exam on Wednesday and Friday this week. It does cover Chapters 1 and 2, so however far we get in Chapter 2. But since it covers the 2 chapters, you could now start reviewing Chapter 1 if there's content in Chapter 1 you want to review. Alrighty. I know you all have questions about the exam, and I'll have more information about it. Are there questions about anything else before I get started? Okay. I'm going to go back. This is where I ended the video just talking. Oh, no, it's not where I ended the video, but I did talk about this in the video. And this is keeping track of sig figs when you're doing a density calculation. So remember, density is mass over volume, and the precision of a density of a sample is dependent on the precision of the mass measurement and the volume measurement. So in this example, mass was measured to 6 sig figs, volume was measured to 3. Since we're doing division here, we keep 3 sig figs in the density that we report. I have this slide here just overviewing steps for doing quantitative problems, so any problems that involve numbers and calculations. As you're going through, like when you were working on the Achieve homework that was due this morning, you probably were following this process. But this kind of step writes all of the steps out and outlines everything that might be helpful as you work on questions in the future. So determine first what is being asked. What's the question? What are you supposed to end with? This could be units that you're looking for, or a quantity, or both. And then visualize the problem. For some problems, it's helpful to draw pictures to visualize what's going on, and just to illustrate what's taking place. If a chemical change is occurring, you might draw molecular pictures. And then organize your data, thinking about what's available. So usually there's more than one piece of data that's provided in a question statement, and then anything else that you need, like conversions or equations. Think about what concepts are required, and then manipulate equations to be able to reach your final answer. Do y'all have a question? I hear a lot of chatting going on right now. Yes.
So, working on the Macmillan homework for significant figures, what about trailing and leading zeros? Because there were a couple questions out there where I was kind of confused on which zeros were significant or not, because I tried a ton of different combinations and stuff, and it was just wrong.
Okay, you can send me specific questions, like of the Achieve homework, but we have all of that summarized in this slide here. I didn't use the term trailing zeros, but it's the same concept. But where are we? Okay, we're going to jump right into an equation. So we are computing the density of a block. It measures 4.4 centimeters by 3.3 by 5.7, and we're given its mass. So remember, density is mass over volume. So using the information that's provided, calculate the density of this block. Okay, so density is mass over volume. What is our mass that we're working with? Okay, yes, this one's just provided to us, 103.4 grams. And then how about volume? 37.764. How'd you get that? Oh, but how'd you calculate it? Yes, okay, so these measurements that are provided are the length, width, and height of the block. So we can multiply all three of these together. I'm going to include that in this fraction. So the denominator is 4.4 centimeters times 3.3 times 5.7. You can also calculate this separately and put that in the denominator. And then what do we get for the density? Okay, 1.178, is that what you said? Did others get that? I don't have my note with me, so I actually don't know. 1.249. Others? Okay. 1.249 grams per centimeter cubed. And then how many sig figs are in the product here? How do we know there's two? The denominator would have two, yes. For the volume, we have three measurements that each have two sig figs. We're multiplying all of them together, so the denominator should have two sig figs. So then our answer should be 1.2 grams per centimeter cubed. Yes.
So like, what if you get rid of that? What if we just wrote volume already multiplied that?
Yes. Okay, so good question. So if we have 103.4 grams, and then what did you all get for the volume calculation? 82.764. Okay, so this is a case where you can do this calculation first, and you have mass over volume of 82.764. We don't round yet. You don't round until the very end. So we know that we should have two sig figs in the final answer because of the two sig figs in the calculation. But if we were to round to 83 here, then we would end up with a less accurate density. So we keep extra digits here, and then we round to two sig figs at the very end. Okay, I noted at the end of the recorded lecture that that density can be used as a conversion factor. So if you know the volume of a sample, you can find the mass of that sample by multiplying by the density of grams over volume, or mass over volume. Or if you know the mass, you can then find the volume by flipping density to be volume over mass, and then you end up with the volume of that. So we have, I think, first an iClicker question. Yes, so let me start this. So this question will be pushed to your devices. We have 0.71 grams of silver in the density of silver. How would you find in 0.71 grams what the volume is of that sample? Are you all getting this question to your devices? Okay. Okay, we'll do 40 more seconds. So when it says a minute 30 up there. And it might be helpful to write out the equation instead of just trying to visually see it. Ten more seconds. Okay, I'll do 20 more seconds. Don't have a lot of responses yet. So 140, then we'll stop. I have half of you all are responding. All right, 5 more seconds. All right, I'm ending it here. Let's see what we're looking at. Okay, we have a mix. All right, so we are provided that there is 0.71 grams of silver. And we want to find the volume of this. We have the density is 10.5 grams per milliliter. Grams is mass, milliliter is volume. So we want to cancel out the units of mass. So we would write 10.5 grams per 1 milliliter. And this will give us the volume of 10.5 or 0.71 grams of silver. So this one's C. Okay, we're going to do another example. I'll have you all work on this one. The last slide of this packet, I will go through kind of quickly, and then we'll move to chapter 2. But let's do this one. So we have a question about mercury, which is liquid at room temperature. You all should look up videos of mercury. It looks really cool. It looks like water. It's not a very thick substance, but it's super shiny like a silver metal. So I recommend looking that up. But anyways, don't do that right now. We have the density of mercury as 13.55 grams per centimeter cubed, and we want to know the mass of a mercury sample in 1.2 cups. So 1.2 cups, that's a volume, and then you will need this conversion that I don't have right now because I forgot my sheet, so let me look it up. Thank you. Oh, I have 1 cup is 236.588 milliliters. I think you already did the conversion. Okay, so 1 cup is 236.588 milliliters. We have 1.2 cups, so how many grams is that? So let's work on that question for a few minutes. Also, are there any questions about this or the last slide? Yeah.
So how many centimeters cubed are in 1
Oh,
Don't we also need that?
yes, I think it's the same. Hold on, let me look this up. Or is that what you were giving me? No, it is the same.
Oh, they're the same.
Yeah. Yes. You will use, yes, so we're given cups as the volume. So we need to convert that to centimeters.
Yeah.
And then you can find the mass. Okay, let's start going through this one together. We have 2 conversions that we're using. We're going to use density as a conversion, and then the 1 cup equals 236.588 cubic centimeters as a conversion. But the measurement that we're provided is the 1.2 cups. So we have 1.2 cups of mercury. We're aiming to get to grams. Before we can use the density conversion, we need to convert cups to centimeters cubed. So that way our units of volume are in the same unit as the density conversion. So we can use 1 cup is equal to 236.588 centimeters cubed. And then this way we can cancel out the unit of cup. So we have a certain amount of centimeters cubed, that's the volume, same volume as 1.2 cups, just in a different unit. And then now to get to grams, so to get to mass, we can use the density. So 13.55 grams of mercury are in every 1 cubic centimeter. So if we have 236.588 cubic centimeters, then how many grams is that? You'll all have to tell me because I don't have my calculation. What'd you get? Without sig figs, I think it was 3,846. And then what's the decimal? Okay. So this is what you should get in your calculator. That looks right to me. But now we have to figure out sig figs. Okay, so we have, how many sig figs are we starting with in the measurement? 2. And we have a conversion conversion, so we don't worry about sig figs here. We say they have infinite sig figs, and then we have 4. Since we're doing multiplication, we keep the 2 sig figs. So we have 3,800, or in scientific notation, 3.8 times 10 to the 3rd grams. And 2 sig figs, because of this measurement here, that has 2 sig figs. Okay, the question was, because there's a conversion factor, why is 1.2 counted? That's because the sample is measured at 1.2 cups. So that's a measurement that's provided to us. Yeah. The cup to centimeter cube conversion, that we don't worry about sig figs. And then density, we do care about those sig figs, but this density measurement has 4, which is greater than 2, so we stick with 2. Other questions about this one? Yeah. 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 I will let you know if there are any that you need to know by Wednesday. But for the like this, I would not expect you to remember. Sometimes, yes. You'll be asked specifically to put it. Yeah.
Unlike quizzes and tests, will we be given conversion factors?
Yeah.
So like 1 cup equals.
This one you'll be given. If there are any that you need to remember, I will let you know on Wednesday. All right. This next one, I will go through, but let's read it together. So we have a graduated cylinder filled to 25.0 milliliters with water. A silver bead is dropped into the graduated cylinder and the water rises to 27.0 milliliters. So if we have beaker with water, this is at 25. We have beaker, those should be the same size. Silver bead is now in it. Now we're at 27.0 milliliters. Okay, the bead's mass is 21.00 grams. Calculate the density of silver. So remember, density is mass over volume. We're given the mass is 21.00 grams. And then to find the volume, we use the other information that's provided here. So if we had a beaker with 25 mils of water, we add silver that has a certain volume, and the volume of the water plus the silver is now 27.0 milliliters. Then the volume of the silver is 27.0 minus 25.0. So to simplify this, we have 21.00 grams over 2.0 milliliters. If we calculate this, this is 10.5 milliliters. And then we have to think about sig figs. What's our sig figs here? How many? Why is it 2?
There's 2 sig figs.
2 sig figs in the denominator. All right. So then we have 11 milliliters. Oops. As the final answer. And that's it for chapter 1. Any questions before we go to chapter 2? Yes.
For the test, how many, like the trodes, like Pico and Nano?
Yes.
And all this, like, how much of that would be needed?
That I'll tell you on Wednesday. Yeah.
Would the unit be milliliters or grams?
Yeah, it is. You're right. It's grams per milliliter. Thank you. No. So centimeters cubed is volume, but a milliliter is just volume on its own. Yeah. All right. Let's go to chapter 2. All right, chapter 2 is all about atoms and the periodic table. There is a lot less math in chapter 2. Maybe that's good for some of you. Some of you may be less excited, but there is less math in chapter 2. That's not to say that what we've learned in chapter 1, that's going to be important in other chapters. But this chapter is really focused on elements, atoms, periodic table. So I have the sections of chapter 2 here. We'll first learn about chemical symbols and then the laws of chemical combination, so how atoms can come together to form a molecule or form new molecules. The history of the atom, which is really how scientists discovered the atom and what's in an atom. We'll talk about subatomic particles, so protons, neutrons, and electrons, isotopes, and ions. Ions are charged atoms. Talk about atomic masses, and then the periodic table, so different sections of the periodic table and what we can identify about elements based on where they are in the periodic table. So here are the chapter 2 learning goals. I won't read them now. I'll read them when we get to each section that covers the different learning goals. But again, this is a way to keep track of what you're meant to be learning in the different sections. So first section, chemical symbols. The goal here is to be able to recognize the symbols for commonly used elements. In the PowerPoint, I outlined which elements you should remember. So we'll get to that in a couple of slides. We use chemical symbols in chemistry, in biology, in science to abbreviate the names of elements. In a chemical symbol, the first letter is always capitalized, and then in some chemical symbols, there are 2 letters. The second letter is never capitalized. These are what's used in chemical formulas. So we've talked a lot about water, H2O. We're familiar with that compound. That compound is H2O because there are 2 hydrogens, which is element H, and 1 oxygen, which is element O. So many of the chemical symbols align with the English name for that element. So I have some examples here. Just going across, we have carbon, which is C, hydrogen is H, oxygen, nitrogen, sulfur, silicon, phosphorus, and neon. All of those align with the actual name of that element. Others do not align with the English name. So W is tungsten, AU is gold, AG is silver. So those are ones that don't align with the English name. On this next slide, I have a table that shows the basis for those symbols. So gold is AU because in some other language, gold is Aurum, or in the past it was called Aurum. You don't need to know this column, but for the elements that are listed under elements that you should remember the symbols for the elements. So the next couple of slides have elements to remember. They are in different groups. We'll talk later in the chapter about how to identify these different groups on the periodic table. You are given a periodic table on all of the exams. So that periodic table, though, only has a chemical symbol. It doesn't have the actual full English name. So a couple of slides here show the different elements that are important to remember. Well, there are some elements that we're going to talk about a lot, and those will become second nature pretty quickly. But the reason it's important to remember these is that when you get into your future chemistry classes, your instructor and classmates, mostly your instructor, will be assuming that you all remember these different elements and not explaining the names that are behind them. So it's kind of like being able to communicate really in chemistry, scientific communication. This is knowledge that should be remembered. Okay, so a couple of slides of elements to remember. A lot of these we're going to talk about a lot. And so you'll get a lot of practice using them. These chemical symbols are what are used in chemical formulas to identify compounds or to communicate which elements are in that compound. So chemical formulas give the relative number of each element in a compound. So we've talked about water. Once again, water has 2 hydrogens and 1 oxygen. So that's why we put the 2 after hydrogen. Ammonia has 1 nitrogen and 3 hydrogens. Carbon dioxide is 2 oxygens and 1 carbon in that compound. Some other examples, CH4, so 1 carbon bonded to 4 hydrogens, that's methane. This other example has, sometimes we see these parentheses. When you have parentheses, whichever number is after the parenthesis applies to each element within it. So in this molecule, in this compound, this is sodium. So we have 1 sodium atom, 2 nitrogens, and 6 oxygens. That's what the statement says down here. We'll talk a lot more about compounds and formulating compounds in chapter 3. Okay. Questions so far? Well, I have a question for you. What's the difference between CO, where both letters are capitalized, and CO, where only the C is capitalized? I'll give you all a second to identify what each of these are. Okay, will someone tell me what CO is where the O is not capital, the O is lowercase? Go ahead. Cobalt. Okay, if we go back a couple of slides, in the transition metals, we have cobalt here, which is element CO. So if the O is not capitalized, we're communicating that we're talking about element CO, which is cobalt. And then how about CO, where both are capitalized? Carbon monoxide, there's a carbon atom and an oxygen atom. So this is 2 elements bonded together. One carbon element, 1 carbon atom, and 1 oxygen. This compound is called carbon monoxide. We haven't talked about naming, so totally okay if you don't know the name of that. So we have 1 carbon and 1 oxygen. When both are capitalized, that's a carbon and an oxygen. When it's CO, O is lowercase, that's cobalt, which is 1 element. Okay, now we're looking at chemical symbols and identifying the name of these elements. This is a iClicker, so let me get this started. 2 questions, so each of these are coming up as individual questions. There are a couple of options to answer. So I'll give you all about 2 minutes to do this. And again, if you have any questions, let me know. Are you proud of yourself?
Yeah.
All right, 20 more seconds till 1:50. 1 minute 50 seconds up here, and then I'll end it. All right, ending it now. All right, looking good. Fe is element iron, so this is one that does not align with the English name. So that's one to remember. That's iron. F is fluorine. And then Si is silicon. That one aligns with the English name. And then Ag is silver, which does not. Silver and gold will start with A. Silver is Ag, gold is Au. Silicon is Si, and then fluorine and iron. Okay, questions before we go to the next chapter? Again, I hear a lot of chatting. That's something that I do not like while I'm talking. When we do the iClicker questions or other practice questions, that's a good time to talk to other people in the class. No questions? Okay, so we are now going to talk about laws of chemical combination. So how we know that atoms can come together, what it means when something goes through a chemical reaction, what atoms are left over, things like that. So we'll learn about laws of chemical composition and then calculate quantities involved in combinations of elements. So when you're burning a match or burning, like you have a bonfire and you have logs burning, it might appear that mass is lost. So we burn the logs and then we just have ashes left over. That's a lot less mass than the logs that we start with. Or if you're burning a match, the match has more mass at the beginning than after it's burnt for a while and fires out. It's a smaller item. So it looks like mass is lost. That's actually not the case. Everything that's burned is converted to different compounds or different elements. And so those are gaseous. When we burn something, we have gaseous carbon dioxide and water. And so if we were to calculate all of the carbon dioxide and the water that's generated and add what's left over in this match, that would equal the mass of the original match before we burn it. So this is the first law, that mass is conserved in chemical reactions, the law of conservation of mass. So mass is conserved during physical and chemical transformations. Remember, physical is like melting, freezing, condensing, those different changes, heating it up. And then chemical is when you're actually burning something or it's reacting with another element. In either of those transformations, mass is conserved. And we can also track the number of atoms in a chemical transformation. For each element, the number of atoms is conserved in the chemical reaction. So the number of atoms for each element that you start with is the same number of atoms that you end with for each element, but they can recombine into different compounds. So in this example, we start with methane, CH4, that reacts with 2 oxygen molecules. So we start with 4 hydrogens, 1 carbon, and 4 oxygen atoms because we have 2 O2 molecules. These react to form carbon dioxide and 2 water molecules. So we have 1 carbon in carbon dioxide. We have 2 oxygen atoms here in carbon dioxide. We have 2 water molecules. We have 4 hydrogen atoms total and 2 oxygen atoms here. So you should add this in. So we start with 1 carbon, we end with 1 carbon. We start with 4 hydrogens, we end with 4 hydrogens. We start with 4 oxygens, we end with 4 oxygens. That's always the case in every chemical reaction. So number of atoms is conserved. As a result, mass is conserved. We have the same number of molecules. Back in the 1700s Antoine and Marie Anne Poltzy Lavoisier is maybe how you pronounce it, I don't know. They did this experiment that proves this law of conservation of mass. So they put phosphorus with some water and of course air in this closed container. So anything that produces a gas would remain in this closed container. They measure the mass of what's present here. The phosphorus reacts with oxygen in the air to produce phosphorus oxide. There's still some water and there's still air, but there's less oxygen in the air. But in total, we have the same mass. So if you're keeping everything contained, you would measure the same mass throughout a chemical reaction, even though we have new molecules being created. Another thing that researchers noticed is that elements combine in specific fixed proportions. So if we have 4 atoms of carbon in this first example and 4 atoms of oxygen, they combine to form carbon monoxide. And for every 3 grams of carbon, there's 4 grams of oxygen in every carbon monoxide molecule. If we have more oxygens, they form carbon dioxide. That's what's represented here. Then there's 3 grams of carbon. There's 8 grams of oxygen. So there's a different ratio of carbon and oxygen in these different molecules. So observations like this led to the development of atomic theory, which we'll cover in the next section. But this explains why atoms combine in fixed proportions. So this next slide here, we have the next law of chemical combination, which is the law of definite proportions. I think in the first lecture, we talked about how water is always 88.8% oxygen and 11.2% hydrogen by mass. So any given compound is composed of a definite proportion by mass of its elements. So let's calculate. We have the proportion for water, but let's actually do the calculation for water. And then in the next slide, we'll do a more complicated one. So water is always 88.8% oxygen, 11.2% hydrogen by mass. Let's actually do this calculation to show that. So to do that, we identify the mass of each element in the molecule. So if you look at, I know you don't have a printed periodic table, but if you look at hydrogen on the periodic table, you'll see its mass is 1.001. We're going to use the unit atomic mass units. We'll talk about these units later in the chapter. For now, that's our unit, AMU, atomic mass unit. If you look at oxygen on the periodic table, its mass is 16.02. We have 2 hydrogens in water. So the the mass of hydrogen in water, so let's see, H mass in H2O is 2 times the mass of hydrogen. So 2.002 atomic mass units. So that's the elemental mass of hydrogen in water. There is only 1 oxygen in water, so its elemental mass is the same as 16.02. So we have elemental mass, we need total molecule mass. Which is 2.002 for 2 elements of hydrogen plus 1 element of oxygen, which is, or 1 atom of oxygen, 16.02. Okay, so the total mass of 1 water molecule is 18.022 atomic mass units. To find the percent by mass for each element, we do the elemental mass divided by total molecule mass. So percent hydrogen, there's 2 hydrogens, so we use 2.002 divided by molecule mass times 100%. When I did this earlier, I got 11.1%, which is 1% off from what's provided. It's probably a result of different sig figs being used throughout the equation. You can follow the same process, do 16.02 divided by 18.022 times 100%, and you should get 88.8 or 9% oxygen. No matter how much water you have, 11.8% of that mass is hydrogen atoms. Question here. Okay. We will do an example here. So now we're looking at sucrose. This is table sugar. We have carbon, hydrogen, and oxygen in sucrose. I need you to change some numbers because I typed this one too fast. So let's do, instead of 324 grams of sucrose, 342 grams. And then instead of 114 grams of carbon, 144 grams carbon. Okay, using those revised numbers, calculate the percent of each element by mass. So we know in a 342 gram sample of sucrose, there's 144 grams of carbon. So we can calculate the percent of sucrose that is carbon using those values there. I'll give you all a minute to work on that, and then we will do the question on the next slide as well. Okay, did anyone do carbon? Or hydrogen or oxygen? Oh yeah, go ahead. So how did you calculate carbon? So the mass of carbon divided by the total mass of sucrose, we'll multiply that by 100%, and you should get 42.1% carbon. Follow the same process for the rest. So we have 22 grams of hydrogen divided by total mass times 100%. We have 6.4% hydrogen. And then 176 grams of oxygen divided by total grams. So any amount of sucrose, table sugar, is 42.1% by mass carbon, 6.4% by mass hydrogen, 51.5% by mass oxygen. Last question I want to do before the end of the day, which is an iClicker question that will be sent to your devices. We have a different sized sample of sucrose. What is the mass of carbon in that sample? You'll use the information we have on the last slide.
the ratio to the single yeah. Yeah. So you could also translate to person.
Okay, I'm gonna stay until I have more of you all submitting this question. But this is where we'll end for today. We'll review this at the beginning of class on Wednesday, and then we'll start the next section. Yes, I am. And then I think Professor Cunningham for the I don't know. But they're such Thanks. Have a good day. Everyone submit? Anyone? Okay, I'm stopping it now. Just making sure you all submit. Thank you, you too. Bye-bye. Hi.
I'm having a problem like knowing which ones I'm like supposed to multiply.
Okay.
Like I know like if I start with grams on the top, then it would be on the denominator.
Yes, we're trying to cancel.
Yeah, but like I'm confused on
Thanks.
which one would I put like afterwards. Like would I put the like for example, I know where like you to get to the grams, like for example, like I'm just like random. To get to the grams, you like use like milliliters or something. Like how do I know
Sorry, I'm
that?
just trying to.
No, you're fine.